All right, guys, let's talk about analyzing polynomials. So here we're going to analyze the polynomial 7x cubed minus 6x plus 4. And we're going to notice some of the important features. To be consistent with your previous math classes, this is going to be a 10-step analysis, and we're going to have it's going to be a very wholesome review of what's important for a function. So we'll start off with the graph. Step number one, always graph it. When you have a graph, it's important to note a couple of things. Look at the shape of it. How many times does it turn? Where do the ends go? How many times does it cross the x-axis? Of course, the y-axis it'll cross it once. But just get a feel for the shape of the function. Make sure this is a good point to check your zoom. Make sure you're zoomed out enough or zoomed in enough. Okay, so graph check. The next thing that we're going to look at is a table, and I've already come up with a table right here. You can usually just go right here to edit list and convert to table. Okay, and I mentioned that for step 2, let's talk about a table with a common difference. So one of the things that we fail to do with functions other than linear is look at their patterns, right? With linear, we see a very obvious pattern in tables, right? Not so much with other types of polynomials. So let's take a look at this. If I go from -40 to +3, I essentially went up 43, right? If I go from 3 to 4, I went up 1. From 4 to 5, I went up 1 as well. And from 5 to 48, I went up 43. Okay, now that's kind of interesting, right? Let's take a look at the difference between those terms. So from 43 to 1, you had to go down 42, right? From 1 to 1, well, that's 0. And to go from 1 to 43, you got to go up 42. Okay, so that's kind of, we see some symmetry right there. Let's check it again. To go from -42 to 0, all right, from -42 to 0, I have to add 42, right? And then to go from 0 to 42, once again, I have to add 42, all right? So this is why I say it. I have now found the third common difference. The third common difference of this polynomial is 42, which is pretty neat, all right? We didn't see that when we first look at that list of numbers, but that is a third common difference, okay? Moving right on along. The third step, as usual, is to do an evaluation. All right, evaluations continue to work in the same way. You can take any point in your table, and let's say, well, if I check L of 2 is supposed to be 48. Let's actually evaluate that. So that's 7 times 2 to the third power, or minus 6 times 2 plus 4. All right, gives you 48, and that's because 2 cubed is 8. 8 times 7 is 56. 56 minus 12 is 44, and 44 plus 4 is 48. So that's knowledge of an evaluation that you need to know how to do by hand. All right, moving on along. Zeros. Your zeros are -1.162. Your y-intercept is 0.4. Continuing. Step 5, domain intervals where this is increasing or decreasing. This is important. The function is increasing. Always read your function left to right. The function is increasing from -infinity. All right, so I'm going to actually write that out. All right, the function is increasing. We're going to use interval notation from -infinity all the way to this point. All right, which was, let's just verify, -0.53. So it's increasing all the way to -0.53, right? Then it decreases from -0.53 all the way down to, well, let's check it. Again, these are domain intervals, so I'm only looking at my x, to +0.53, all right? To +0.53, all right? And then once again, again, at that turning point, it's going to start increasing from 0.53 all the way to +infinity as far as my x values go. So that is domain intervals that increase. Domain intervals that are positive or negative. Well, it looks like this whole, for this, we're going to look at right here, this 0, okay? And basically, we're going to determine that, and that 0 is at -1.1, that the function is positive from the function is negative from -infinity to -1.1, and then the function is positive from -1.1 all the way to infinity.